Welcome to the lecture series on CFD Part 1. This is lecture 18 on simple and related methods for the solution of Navier-Stokes equations. This lecture is about simple and related methods for the solution of Navier-Stokes equations. This class of methods is most frequently used in both commercial and public CFD codes. After an introduction to principles behind these methods, 4 algorithms are described in detail: simple, SIMPLEC, simpler, and PISO. There are more versions of such algorithms in literature, but they differ only in small details. It will be shown that even the fractional step methods are not much different from simple type methods. They are all based on the same idea. First, predict the new velocity using a suitable estimate of the pressure field, then correct velocity and pressure to enforce the continuity constraint. Such methods are also called projection methods. While fractional step methods always march in time toward a steady-state solution, simple type methods drop the rate of change term altogether and use an under-relaxation parameter to promote convergence of outer iterations in a single infinite time step. It will be shown that this practice is related to time marching with a time step that varies within the solution domain. Finally, a complete step-by-step discretization and solution process using collocated grids and simple algorithm is presented, including the derivation of pressure correction equation. A computer code in which all these steps can be identified will be provided as a supplement to lectures 19 and 20. Simple and related algorithms are usually used with fully implicit time integration methods, first-order implicit Euler or second-order quadratic backward. They can also be used with Crank-Nicolson or any other implicit scheme. 4 algorithms from this family are described here with second-order quadratic backward fully implicit scheme. Fluxes and source terms are computed at the new time level Tn plus 1. Odd solutions appear only in the unsteady term. Outer iterations within time step are used to update nonlinear terms, deferred corrections, and the effects of solution-dependent fluid properties, which is especially important when turbulence models are used. The methods are also suitable for steady-state flow problems. They simply assume an infinite time step, but time marching towards steady state is also possible. With quadratic backward time integration scheme, convection, diffusion, and source terms are computed at the new time level Tn plus 1. The momentum equation to be solved at this time level is given here. Solutions from 2 previous time levels appear only in the approximation of time derivative. Because outer iterations are performed within a time step, we use the iteration counter m to denote estimates of the solution at the new time level. When momentum equations are discretized using a finite difference method, the algebraic equations to be solved at outer iteration m for the velocity component ui look like this. Qp contains all explicitly treated terms except for the pressure gradient, which is shown here separately. In the predictor step, U star is computed first using pressure from previous outer iteration. We split the matrix A into a diagonal part, AD, and an off-diagonal part, AOD, and rewrite the above equation in symbolic notation as shown here. The velocity field needs to be corrected to enforce continuity by correcting the pressure. The corrected pressure is denoted by 1 star and corrected velocities by 2 stars. The relation between velocity correction and pressure correction is obtained by requiring that corrected velocities and pressure satisfies this simplified form of the momentum equation. Note that velocity is corrected only in the diagonal part, that is, only at the cell center, not at neighbor nodes. This simplification requires under-relaxation of pressure correction. We now subtract the equation which was solved for U star from this equation to obtain this expression for velocity correction as a function of the gradient of pressure correction. We then require that corrected velocities satisfy the continuity equation and express velocity correction via pressure correction, which leads to the following equation for pressure correction. This is a Poisson-like pressure correction equation. The form is similar to the equation in implicit fractional step method presented in lecture 17, but here the spatial variation of diagonal elements in the coefficient matrix from momentum equation also play a role, because the inverse of the diagonal element is inside the divergence operator. Once pressure correction equation is solved, velocity is corrected and we set um equal u2 star. Because a simplified form of the momentum equation was used to derive the relation between velocity corrections and pressure correction, only a fraction of p prime is added to pm-1. Typical values for alpha p are 0.1 to 0.3 for steady state flows and 0.3 to 1 for unsteady flows. The smaller the time step, the higher value of alpha p can be used. A nearly optimal relation between under-relaxation factors for pressure and momentum equations in steady state flows can be derived. Alpha p equal 1 minus alpha u. One way of deriving this expression will be presented in slide 13. Many variants of this method were developed with the aim to correct the error introduced by neglecting the effect of velocity correction in off-diagonal terms. 3 of them will be presented in the following 5 slides. Let us now see how the effect of velocity correction in off-diagonal terms can be approximated rather than neglected. This is the momentum equation solved to compute V star with pressure taken from previous auto iteration. This is the momentum equation which we would like to satisfy with corrected velocity and pressure. Velocity is here corrected in all terms. When we subtract the first equation from the second one, we obtain the following relation between velocity corrections and pressure correction. Simple algorithm neglects the second term on the left-hand side to obtain a direct relation between velocity correction at the grid node P, or cell center, and the gradient of pressure correction. SIMPLEC algorithm approximates this term by assuming that velocity correction at one node is close to a weighted average of velocity corrections at neighbor nodes. This allows us to express the product of coefficients and neighbor velocity corrections as the product of velocity correction at node P with the sum of neighbor coefficients. In this way, we obtain again an equation in which only the velocity correction at node P and the gradient of pressure correction appear. With the introduced approximation, the relation between velocity correction and pressure correction becomes simpler, given by this expression. We now require that corrected velocities satisfy the continuity equation and express velocity corrections via pressure correction. This leads to the following pressure correction equation. It has the same form as in simple algorithm. The only difference is that we add to the coefficient on the main diagonal the sum of off-diagonal coefficients. For steady-state flows and conservative discretization, the following relation between matrix coefficients in the momentum equation holds. The coefficient for node AP, that is on the main diagonal, is equal to the negative sum of the neighbor coefficients divided by the under-relaxation factor for velocities, which is smaller than unity. Without under-relaxation, these two terms would give 0. By approximating rather than neglecting the off-diagonal terms, we reduce the magnitude of the multiplier of pressure correction gradient in the expression for velocity correction. Thus, for the same velocity correction, SIMPLEC algorithm produces much smaller pressure correction than simple, and an under-relaxation of pressure correction is not required. In simple algorithm, the first step is identical to simple. Velocity is corrected and we set equal u2 star, but we do not correct the pressure with the computed pressure correction. Instead, we want to compute the pressure such that the momentum equation in which all terms are corrected is satisfied. We take the divergence of this equation to obtain a Poisson equation for pressure, from which the final value of pressure at auto iteration m is obtained. This method has not become popular for two reasons. The computing effort is doubled compared to simple, and boundary conditions for the pressure equation are problematic. Another possibility to improve on simple is to follow with a series of further corrector steps. Step 1 is the simple predictor plus first corrector. Corrected velocity components and pressure satisfy this equation. Step 2 is the second corrector. We add one more star in each term and subtract the upper equation from the lower one to obtain the expression which relates the yet unknown second velocity correction, the known first velocity correction from previous step, and the unknown second pressure correction. Because in off-diagonal terms the known first correction features, we obtain a direct relation between the second velocity correction and second pressure correction. We then request that the velocity v free stars after the second correction also satisfies the continuity equation. Because v with 2 stars already satisfies the continuity equation, only the divergence of the second term remains. We express the second velocity correction using this expression, which leads to the following equation for the second pressure correction. The coefficient matrix in this equation is the same as in simple predictor, only the right-hand side is different. It is computed from the first velocity correction, which is now known. Upon solving this equation for p double prime, one can compute v double prime, correct velocity and pressure, and continue with more corrector steps if desired. Just add one more star and prime. PISO algorithm has become popular as a non-iterative method for unsteady flows. Momentum equations are solved only once per time step, followed by one predictor and several, circa 5 corrector steps with pressure correction equation. The original version is first order in time because mass fluxes in the momentum equations are based on the velocities from previous time step. A second order version was published by Tukovic et al. In 2018. The mass flux is computed using velocities advanced by an explicit Adams-Bashforth scheme as in explicit fractional step methods. Because of the explicit part, the second order version has a lower limit on usable time step size for stability reasons, which may cancel the advantage of performing no iterations on momentum equations. In lecture 20, the performance of different algorithms will be analyzed and compared. Let us check under which conditions simple performs like SIMPLEC. We require that both algorithms produce the same velocity correction and compare the gradients of pressure correction. As mentioned in slide 9, in steady state flows, the central coefficient in momentum equations is equal to the negative sum of neighbor coefficients divided by the under-relaxation factor. When we replace the sum of neighbor coefficients by AP times alpha u, then AP cancels out in numerator and denominator, leading to this relation between the gradients of pressure correction in simple and SIMPLEC. Thus, for the same performance, that is, velocity and pressure corrected by the same amount, the pressure correction computed by simple method should be multiplied by alpha p equal 1 minus alpha u when correcting pressure. This expression can be derived in different ways. Typical under-relaxation factors for steady-state flows are alpha u equal 0.7 to 0.9 and alpha p equal 0.3 to 0.1. The figure on the right shows the flow chart of simple-like methods. We start a new time step by initializing variables either with the solution from previous time step or with an explicit predictor, one of the Adams-Bashforth schemes. We then start outer iteration loop by solving momentum equations using available estimates of mass fluxes and pressure to obtain V star. We then solve the pressure correction equation and correct velocities at cell centers, mass fluxes through cell faces, and pressure to obtain Vm and Pn. We then solve additional scalar transport equations if needed and update fluid properties. We repeat until outer iterations converge, then move to the next time step. In PISO algorithm, outer iteration loop is missing, but there is a loop around pressure correction. Let us now see how SIMPLE differs from the implicit fractional step method described in lecture 17. In the implicit fractional step method with the acronym IFSM, if time step tends to infinity, the source term in the equation for pressure correction tends to 0, which is not the case in SIMPLE. This is the pressure correction equation in IFSM and this in SIMPLE. If we assume that AP does not vary much in space, this equation can be approximated by this expression. The coefficient AP in momentum equations contains the contribution from the time derivative and from convection and diffusion fluxes via off-diagonal coefficients AK. It thus has a finite value even for an infinite time step. However, in that case, the under-relaxation must be applied as shown in slide 13. The IFSM and SIMPLE differ by the contribution from convection and diffusion fluxes in the multiplier of the source term in the Poisson equation for pressure correction and in multipliers of the gradient of pressure correction in expressions for velocity correction. Otherwise, both algorithms operate following the same basic idea of prediction followed by a correction. SIMPLE and SIMPLEC are the most widely used algorithms for computing steady-state flows. They use Navier-Stokes equations without the rate of change term, but have to use under-relaxation to promote convergence of outer iterations, that is, updates of coefficient matrix and forcing term. However, instead of under-relaxation, they can also march in time like fractional step methods. In that case, the matrix coefficient on the main diagonal contains the negative sum of neighbor coefficients plus density divided by time step from the time derivative. If we set this coefficient equal to the one when only under-relaxation is used, we obtain the following relationships between time step and under-relaxation parameter. In the case of time marching, we have the same time step at all nodes, which is equivalent to a variable under-relaxation factor in steady-state computation with an infinite time step. If we use under-relaxation and an infinite time step, then the under-relaxation parameter is the same at all nodes, which is equivalent to a variable time step in a time marching method. In lecture 19, we shall compare the two approaches. Which one is more efficient is problem dependent. Let us now go step by step through the discretization and solution process using finite volume method on collocated grids, quadratic backward time integration method, and SIMPLE algorithm. The continuity equation and the momentum equation for the velocity ui are given here in integral form. The approximations for all terms in momentum equations are the same as on staggered grids, as described in slides 15 to 19 of lecture 17, only that now the same control volume is used for all variables and interpolation must be used whenever a variable value at cell surface is needed. Midpoint rule is used for volume integral in the rate of change term, that is, the density and velocity component from cell center are multiplied by cell volume delta V. The time derivative at Tn plus 1 is approximated by differentiating a parabola fit to variable values at 3 time steps, Tn minus 1, Tn, and Tn plus 1. See slides 21 and 22 in lecture 13. The multiplier of the new velocity contributes to the central coefficient in the matrix, while terms involving known velocities from previous time steps contribute to the forcing term on the right-hand side of the algebraic equation. Because outer iterations are performed within time step, the new values will be denoted by the iteration counter m. The convection fluxes must be linearized. Picard iteration scheme will be used. The new flux is then expressed as the product of the mass flux, which is assumed known, and the convected velocity at cell phase center. The mass flux is computed using midpoint rule for the surface integral over a cell phase, here the east phase, and velocity from the previous outer iteration. The velocities need to be interpolated to the phase center. Linear interpolation is a suitable second-order approximation. The phase velocity that was corrected to enforce continuity in the preceding outer iteration is used to compute the mass flux. The convection flux of UI momentum through the east phase is expressed as the product of the latest estimate of mass flux and the UI velocity at the phase center. For second order accuracy, the latter will be computed by linear interpolation between two cell center values at nodes P and E. For better convergence properties, first order upwind scheme is used implicitly, that is, to compute the contributions to the coefficients in the matrix, while the difference between explicitly computed fluxes using linear interpolation, here labeled CDS, and upwind approximation will be moved to the right-hand side of the algebraic equation. This approach to implementation of high-order schemes is called deferred correction. If the term in brackets is multiplied by a blending factor between 0 and unity, the two schemes are blended. This may be useful when the grid is too coarse for the pure second-order discretization, either globally or locally. To compute viscous forces at cell faces, that is, diffusion fluxes, we need to approximate viscous stresses at cell face centers. At the east phase, we need tau xx for u velocity and tau yx for v velocity. Central difference is almost exclusively used for this purpose. The derivative of u in x direction is approximated as the difference between values at nodes E and P divided by distance. The same kind of approximation is used to compute the shear stress at the east side for v velocity. Velocity values at cell corners need to be computed by interpolation. Linear interpolation is the most widely used second-order approximation. The pressure terms are computed in a conservative way as surface forces. For u velocity, only pressure at faces E and W are relevant on a Cartesian grid, because forces at the other two faces have no component in x direction. For v velocity, pressure is needed only at north and south faces. Pressure needs to be interpolated to cell face centers. Linear interpolation is usually used, but approximation of high order are also applicable. Source terms, if present, are integrated over volume. That is, the value of the volumetric source at the cell center is multiplied by the cell volume. For example, if density is not strictly constant and we use the Boussinesq approximation, in all terms other than the gravity term, density is treated as constant, equal to the reference density. And in the buoyancy term, the difference between local density, which may vary with temperature or concentration, and the reference density is multiplied with gravity and cell volume. This completes the discretization of all terms in the momentum equations. We now need to sort all these terms out and cast them into an algebraic equation involving as unknowns velocities at the center and at centers of the neighbor control volumes. On the left-hand side of the original equation, we have one part of the rate of change term and convection fluxes. On the right-hand side, viscous forces, pressure forces, buoyancy force, and the explicit part of the rate of change term. The net convection and diffusion terms involve the sum of fluxes over all control volume faces, assuming that the unit surface vector at all faces is pointing outward. In the computer code, fluxes are computing only once for E and N phase. The flux at W phase of one cell is the negative of the flux through the east phase of the preceding cell, and so on. Viscous fluxes are split into an implicit part, which looks the same as diffusion flux in the generic equation, and the extra part, whose net effect is zero when fluid properties are constant. For this reason, it is treated explicitly, that is, computed with values from previous auto iteration and moved to the right-hand side of the algebraic equation. Once everything has been sorted out, the usual form of an algebraic equation is obtained where subscript k runs over immediate neighbor cell center locations, east, north, west, and south. The matrix coefficients are the same for all velocity components. They contain a contribution from convection fluxes, here from the first order upwind approximation and from implicitly treated part of viscous forces. For all conservative methods holds the coefficient on the main diagonal is equal to the negative sum of neighbor coefficients plus the contribution from the rate of change term. For large time steps, under relaxation is applied as described in slides 5 to 7 of lecture 11. The net source term is computed by adding pressure and buoyancy forces, deferred correction part of convection fluxes, the explicit part of viscous forces, and the contribution from the rate of change term. When we solve the momentum equations at the outer iteration m, using the above defined coefficient matrix and source vector, we obtain the velocity field v star. In general, this velocity field does not satisfy the continuity equation. When we compute mass fluxes through control volume phases using the formula from slide 18 and velocity v star, and sum them over all control volume phases, we obtain a mass imbalance. The mass fluxes need to be corrected to eliminate this imbalance. For this purpose, one can use either simple type algorithms or fractional step methods. Here, simple algorithm will be used. For the derivation of pressure correction equation, it is advantageous to work with pressure gradients at cell centers. We can express pressure gradient at cell center via surface pressure forces using the following identity and midpoint rule approximation for the volume integral of pressure gradient. If pressure at phase centers is computed by linear interpolation, this expression reduces to central differences. These expressions show the effective pressure gradients at nodes P and E. To compute mass fluxes through cell phases, we need to interpolate velocities to phase centers. Linearly interpolated velocity at a cell phase center is corrected by replacing interpolated pressure gradient with a gradient computed at cell phase center. The over bar denotes interpolation. This is known as Rien-Chow correction, which is introduced to couple the velocities and pressure more tightly, like on staggered grids, and avoid checkerboard oscillations. Let us have a closer look at the Rien-Chow correction. The difference between linearly interpolated pressure gradients from cell centers, approximated by central differences, see previous slide, and locally computed pressure gradient using central difference approximation is given by this expression. This is proportional to the central difference approximation of the third pressure derivative at cell phase center. Second derivative at node E minus second derivative at node P divided by distance between them. When central difference approximations for second derivatives are used at nodes P and E, we obtain the following approximation for the third derivative at cell phase center E. By comparing these two expressions, we obtain the following relation between the Rien-Chow correction term and the third derivative of pressure at the cell phase center. This correction is proportional to grid spacing squared. It is thus a second order approximation consistent with other approximations. When we assemble the continuity equation, the divergence operator acting on velocities at opposite phases means effectively the difference between third derivatives at cell phases divided by distance, which is an approximation of the fourth derivative of pressure at the cell center. Therefore, the Rien-Chow correction is equivalent to adding a fourth spatial derivative of pressure to the continuity equation. Following the principle of simple algorithm described in slides 5 and 6, we derive expressions for velocity corrections at cell phases as functions of gradients of pressure correction. See the last equation in slide 22 as follows. Velocity corrections at cell centers look the same. The reciprocal value of the coefficient AP from momentum equations needs to be interpolated to the cell phase center from the two neighbor cell centers. By requesting that corrected mass fluxes satisfy the continuity equation and expressing the velocity corrections via pressure corrections using these expressions, we obtain the following pressure correction equation. The matrix coefficients from this equation are given by these expressions. Note that these coefficients are proportional to the cell face area squared. This means that when cell aspect ratio is high, the coefficients in one direction are much larger than in the other direction. This is, for example, the case in prism layers near a wall. If cell aspect ratio is, for example, 100, then the coefficients in the direction normal to wall are 10,000 times larger than in the direction parallel to wall. This makes it more difficult to solve the pressure correction equation accurately because some solvers converge slowly under such conditions. The solution procedure is as follows. Solve the pressure correction equation and correct mass fluxes, cell center velocities, and pressure. Under-relax pressure correction by adding only an alpha p fraction of p prime to pressure from previous outer iteration. Then update the coefficient matrix and the right-hand side of momentum equations and start another outer iteration. Other algorithms can be implemented accordingly. If the flow is steady, continue with outer iterations until the residual norms are reduced by a prescribed factor relative to the initial value. Set alpha p equal 1 minus alpha u, where alpha u is under-relaxation factor for velocity. If the flow is unsteady, move to the next time step after a prescribed number of outer iterations per time step is performed or a suitable convergence criterion is met. Set alpha p to a value between 0.3 and 1. Use higher values for smaller time steps. Let me briefly summarize this lecture. SIMPLE and SIMPLEC are the most widely used algorithms when solving the Navier-Stokes equations for incompressible flows. At least one of them is available in every commercial and public CFD code. They perform equivalently if optimal under-relaxation is used in SIMPLE. They are suitable for simulating flows which include additional flow-related phenomena like heat and mass transfer or using turbulence models based on Reynolds average Navier-Stokes equations. Additional scalar transport equations are easily incorporated into the outer iteration loop within a time step. PISO algorithm is widely used to simulate unsteady flows because of its computational efficiency, solving momentum equations only once per time step. Being first order in time, it is mostly used when the unsteadiness is imposed by boundary conditions. For example, to simulate flow in an internal combustion engine cylinder with a prescribed motion of piston and valves.